Last topic in this section is going to be divisibility. Divisibility suggests that if we have any integers a, b, and c, we have a statement a slash b. So it's not a such that b, but in this case it means a divides b, which means one of four possible ideas. First of all, it means that b can be written as a times c, where a and c are integers. And I'll give you an example of that. We know that 2 divides 6, right? And that means that 6 is equal to 3 times 2. Right? So right here, that just fits that definition. B is a multiple of A. All right, so we know that the multiples of 2, 2, 4, 6, 8, 10, and clearly B is a multiple of A. B divided by A is an integer. Check. A is a factor of B. So this is B, and A is a factor. All right, so that's what we mean by divisibility. All right, all four of these are different ways that we can express that A divides B. Now, for us, the only two that really matter, right, are probably going to be the first and the last. Right, so this one's definitely important, and A is a factor of B is important. The other one's not saying that they're not important, but for direct proof, these are going to be the two most important that we're going to utilize. Similar to integers and rationals, we're just going to start out by proving or disproving a few of these expressions. So for number one, negative 8 divides 48. Well, isn't it true that 48 is equal to negative 8 times negative 6? Right? And hence, it fits the form of B equals AC. Right? Where 48 is B, and then 8 is A, and then 6 is C. Right? So that's nice and easy to be able to verify. All right. Now, number two, 6 divides 13. Well, that's not true because, first of all, we could divide it and it wouldn't be equal to an integer. But another easy way is just to show the multiples of A. All right, so multiples of 6, 6, 12, 18, and clearly 13 is not a multiple of 6. All right, so this is false. All right, and this one's true. All right. X plus 1 divides x squared plus 3x plus 2. We could rewrite this as the statement x plus 1 divides x plus 1, x plus 2 by factoring. And clearly, x plus 1 is a factor of x squared plus 3x plus 2. So this is true since x plus 1 is a factor of x squared plus 3x plus 2. And then finally, x plus 3 divides x squared plus 3x plus 2. Well, that's false because x plus 3 is not a factor of x squared plus 3x plus 2. All right, so that's what we're looking for with divisibility. Show it's a factor, or try to show it's not a multiple, or it is a multiple, or something like that. Try to use any of these four definitions. Right. Now, let's take a look at least one example in this video, and then the next video we'll take a look at two more examples of direct proofs involving divisibility. This is a pretty common one. This is called the transitivity property. For all integers a, b, and c, if a divides b and b divides c, then a divides c. Right? Very common classic sort of proof that we're going to do here. So we're going to start out with the antecedent, which is this, right? And it's conditional if a divides b and b divides c. So definition, we're going to let A, B, C be elements of Z such that A divides B and B divides C. And of course, we want to write such that A, B, C are arbitrary but particular. All right. Now, we're going to use our definitions of divisibility, okay, because we've assumed that A divides B and B divides C. Okay? So, by definition of divisibility, we can say that B, since A divides B, that means A is a factor of B. So that means that B is equal to A times K. B divides C, right? That means that C is equal to B times another integer, right? Since B, that means that B is a factor of C. So we could say that C is equal to BP or something of that nature, right? Now we introduce two new variables. So we're going to say K and P are elements of the integers, right? Now we have to show that A divides C, right? And how do we show that? Well, we know what C is equal to, okay? So let's recall that C is equal to BP. By substitution, we could say that C is equal to, notice that B is equal to AK. So that's going to be equal to AK for B times P. Right. Now, another way that we could write this is we could say C is equal to A times KP is an integer. Let's call K times P, let's call that the integer M. Okay, so where M is an integer, right? And that's by integer closure. All right, now, notice that there's not a lot of algebra in this one, okay? But we did have to use the idea of substitution a couple times, which is something that we haven't seen yet in any of the previous problems, but we're expanding our repertoire at this point. All right. Now, doesn't C contain a factor of A, which means that it's divisible by A. That means that A divides C. All right, so we're done. Okay, so we can say thus, by above, C is equal to AM, and hence C contains a factor of A. This means that A divides C by the very definition of divisibility. Okay? So remember, if C is equal to AM, let's go all the way back up here to our definition, C equals AM, that means that A divides C. All right, so we're just replacing variables at this point. Okay, so pretty cool that that worked out really well. Thus, or we could say hence or whence or whatever you choose to. Thus, for all A, B, C, and Z, if A divides B and B divides C, then A divides C. And again, that's the transitivity of division property, right? And it's an algebraic property. And that makes a lot of sense because let's say, for instance, we have 2 divides 4 and we have 4 divides 8. Those are both true statements. That means that consequently, 2 divides 8, which is certainly a valid statement. And we could go on like this forever, but we've just proven it for any arbitrary but particular values a, b, and c. In the last video in this section, we're going to take a look at two last examples of divisibility, a little bit more rigorous than this one, but not quite so much.